Thank you for coming with me so far. Right now, I'm going to show you a concept map to see how we link everything together. It's always good for you to prepare your own concept map so that you have a good understanding of how different concepts connect to each other. Remember, understanding will help you to have longer remembrance and retention of things. Okay, let's start the story with charge. So charge is Q, and charge is measured in coulombs. Use a different color, which is C. Okay. And if we introduce electromotive force or EMF, V, which is measured in volts, V, if we introduce a EMF to a charge, we can create a flow of charge, which is what we call a current. So current is I, and it is measured in amperes, which is A. Okay. And we know that for flow of charge, there are two ways of naming it. First is if the flow is from positive to negative, that is when we have the conventional current flow, which is usually what we draw in circuit diagrams. But actually what happens is that electrons are actually flowing from negative to positive. So this is what they discovered later, which we call it the electrons flow. So let me have it in a different color so that you can see. Okay, all right. The relationship between current and charge, okay, is symbolized by this equation. I is equals to Q over T. And in this case, T is measured in SI unit, which is in seconds. So current is the rate of flow of charge and measured in amperes. We measure current by the ammeter. Okay, all right. Now, EMF is connected to your charge by this formula, which V is equals to work done to bring per unit charge across the circuit. Okay, and it's measured in volts, right? We have a separate another quantity which is similar to EMF, which we call it potential difference. So potential difference is also measured in volts. Okay, V, let me box it up. Okay, the main difference between EMF and potential difference is that PD is the work done to bring per unit charge across 2 points, where EMF is across the entire circuit. Okay, right? Potential difference is measured using a voltmeter. Okay, so now we have I and we have V. Now comes to the most important equation, the relationship between these two equations. These two quantities is represented by Ohm's law, which is V is equals to IR. Okay, potential difference or EMF is directly proportional to the current flow. Okay, dependent on the R, which is the resistance. R. Okay, resistance is measured in ohms. Okay, sorry, it doesn't need apostrophe. Measured in ohms. Okay, the symbol is this omega, right? Let me box this up. Okay, so far do you see it? Right? Okay, so let's talk about our ammeter now, since we have brought in resistance. So for ammeter, it has very low resistance or close to zero. Okay, so you put it along the circuit, right? Okay, so that is for your ammeter, right? For your voltmeter, on the other end, it has very high resistance. So there is no current flow through it. Okay, So for a voltmeter, you always connect parallel, right? Whereas the ammeter, you can connect it in series. Okay, right? So you have these two words, parallel and series. Okay, now let's talk about these two words. So series connection, okay, is when you have the same pathway. Okay, that's your series connection, right? If I draw it out, okay, it looks like this. Okay, so the main behavior for series connection is that the current flow through every component along the same pathway. I1, I2, I3, I4, they are all the same. Okay. However, potential difference behave slightly different. They are different dependent on each of the resistance. So if this is V1, V2, and this is V3, covering over everything is V4. V4 is equals to V1 plus V2 plus V3. Okay. If we talk about the resistance, R1, R2, R3, total resistance is equals to R1 plus R2 plus R3, so on and so forth. Okay, now let's find some space for the parallel one. Okay, let me bring this up here. Okay, so parallel connection is when we have different pathways. Okay, let me zoom it in for you. So first of all, behavior of current again. I1, I2, I3, I4. I1 is equals to I2 plus I3 plus I4. So when the current hits the junction, it splits into different pathway. But the potential difference across each of the resistors along here will be the same. So let's say if I were to connect a voltmeter here, V1, and this is V2, right? V1 will be equals to V2, right? If I draw another one here, V3, it will all be the same, okay? But for total resistance, the equation is slightly more complicated. 1 over R total is equals to 1 over R1 plus 1 over R2 plus 1 over R3, okay? So far we have our concept maps here. Now let's have the finishing touches. You still remember how does EMF looks like in a circuit diagram, long line and a short line. Okay, long line is your positive sign, short line is your negative sign. Okay, and our resistors look like this. Okay, a square box and a box with an arrow, that is your variable resistor, which we will cover a lot more of it in the next few videos. Right, so this is your overall view of what we have covered so far. Draw your own concept map now.